A Klingon warrior used an inclined ramp to load a crate full of laser guns on board of his spaceship, but a moment of inattention was enough for the load to slide down to the ground. A spy was observing the situation and made a note based on his rough estimations. Ramp had, this is the ramp, had an inclination alpha equals 30 degrees. The ramp height, from here to here, and at this position we have our crate full of laser guns. This height was 15 meters. Time in which the crate slid all the way down, time was 3 seconds. 3 seconds. And we also have the mass of the crate, 100 kilograms. Actually, we won't need this mass because this mass will reduce in the final solution. Find the gravitational acceleration on the surface of the planet Qo'noS. So important information here, it's not Earth, it's another planet, it's a planet Qo'noS, and the question is about gravitational acceleration. So gravitational acceleration is unknown. You may be used to value of gravitational acceleration equal to 10 meters per square second, because that's the standard acceleration at the surface of the Earth. But in this question, in this exercise, in this particular exercise, we don't ask about anything else, but about gravitational acceleration. Gravitational acceleration will be different depending on the planet you are on. It's a different planet, so it's a different acceleration. So don't make an assumption that g in this case would be anything like 10. It will be probably something completely different. So we have our data, we know what to look for, and now some of you consider this exercise as something very unusual, but in fact this is a pretty much standard exercise about a ramp and an object sliding down from this ramp. So let's have a look how to solve it. The first thing is, of course, the composition of the gravitational force. This is the gravitational force of this crate, mg, mass of the crate, multiplied by the gravitational acceleration that we are looking for. This force can be decomposed into two smaller forces. Sliding force, responsible for moving this crate down the hill, and another force which is called normal force. Technically, normal force is actually pointing up from here somewhere there. So this is the force which the surface here acts upon the object to prevent sinking this object into the ground. So it's pushed up to prevent sinking into the ground. This force is perpendicular to the surface. This is called the normal force. But for the geometrical case, it is much easier to consider this normal force as being here. It is exactly the same magnitude or value or length of this arrow here, and only the direction is opposite. How we can calculate this? Probably after a few exercises like this, you will know these formulas by heart. Okay, it's a pretty much standard way of solving this type of exercises, of questions, because we simply identify the alpha angle here. We have a right angle right here. mg, the gravitational force, is hypotenuse of this triangle, and now the normal force and the slide force are two sides of this triangle. So, for example, sine alpha is this side, which is the sliding force, over the gravitational force, over mg. So we can now write all the three main formulas here. The sliding force, from this, it is mg sine alpha. The normal force, this force, it is mg cosine alpha. And from the exercise, we also have another value known. Assume the approximated friction coefficient is 0.2. Friction coefficient F, 0.2. This means that we have friction in this exercise as well. Friction will always prevent the actual motion. If something is sliding down, this means that the friction will try to stop it. So friction is here, and the friction formula is the normal force, the pressure with which the object depresses the surface, multiplied by this friction coefficient. So this is Fmg cosine alpha. These three formulas are something that you can just automatically write each time you see something like this, any type of a exercise in which something is standing on a ramp, either sliding down or maybe pushed up, whatever. These forces will always happen, okay? This is a sliding force which tries to slide this object down. This is the normal force, which we are actually not directly interested in. This normal force is only interesting because we want to know the friction. What's the total force that affects this object in this situation? The total force, or net force, is the sliding force, Fs, minus friction. Okay? No other forces in this case. We have no one pushing this up or down. The Klingon warrior who used to push this plate up is doing something else, and as it is said here, a moment of inattention. This inattention was lack of any additional force. So he's not anymore pushing this up, pushing it up, or pushing it down. So these are the only forces that we have here. You can think about this exercise. Perhaps it's tricky because you have to calculate something which is inside of all these formulas, so we can find the force without knowing. How can I find the force without knowing G? Okay, I would say just follow the standard route. You know these three forces, actually two forces, the sliding force and the friction force. So the net force is something like this. It's mg sine alpha minus fmg cosine alpha. And don't worry that we don't know g at the moment. We know everything else, and probably we won't need too much about this thing. These are forces, okay? The next pretty much standard step is to calculate the acceleration with which this object will slide down, will go down. Acceleration, according to the second rule of motion, is F over m, force divided by mass. We have our force here, okay, and we have a mass here. Before doing this, I will extract this m, mass, okay. Actually, I can extract mg. Both the mg appears in both sides. Mg is here, mg is here, so I can change it into mg bracket sine alpha minus f cosine alpha. over m. You can easily see that m, the mass, reduces. Okay, so we eventually have something like this. Our acceleration is equal to g multiplied by sine alpha minus f cosine alpha. But wait a moment, we know alpha, so we know sine alpha and cosine alpha, and we also have f. So everything in this bracket is easy to calculate. So let's continue this calculation. A equals g bracket sine alpha, it's 0.5 minus 0.2, that's the value of f, okay, multiplied by 0.87, I think this is cosine of 30 degrees taken with sufficient precision. So this is g multiplied by I actually made this calculation, so I will use my previous calculation. It is 0.326 g. Okay, so we know that we have acceleration equals 0.326 g. I need some more space on this whiteboard, so I will wipe some of the formulas out. Okay, I have now some space. I only left this result acceleration. This is the acceleration of this crate while it is going down, equals 0.326 g. And the g is something that we are looking for. G is the unknown value. Of course, we don't know the actual value of acceleration, but once we could find out acceleration, if we know acceleration, we will immediately know the value of g. How can we how can we guess the value of a? Let's look at this thing here. Of course, we have the mass, but actually mass would connect this acceleration with force. It's like going back to stuff that we have already done. We have already considered the forces, the masses, and so on. But we have something that hasn't been used so far, that's time. If I have a time, and what else of input data that we still haven't used, that's the height of the stamp, 15 meters. Here is 15 meters from here to here. As you look at this structure here, it's a right triangle with a height of 15, with the angle of 30 degrees here. We can actually solve this triangle quite easily for finding this distance. Okay, if we say that's the distance x, we can quite easily find the distance which this object actually travels. So we have x, we have distance, we have time. Okay, we need to find acceleration. What kind of formula we should use? X. Okay, x, the distance traveled in accelerated motion, has a widely known formula which says x equals a t squared over 2. And this is exactly what we need. We will know x. We don't know x yet, but it is actually very, very easy to find, because sine alpha is h, the height, divided by x. Okay? Some people made the calculation that if so, x equals h sine alpha. H is 15 meters, sine alpha is 0.5, so x was 7 meters. It's apparently wrong, because the real value of x is rather h divided by sine alpha, okay, and h, 15 divided by half, it's 15 multiplied by 2, so our x equals 30. Okay? If you just look at the picture, if this height is 15, it's totally impossible that from here to here we have 15, from here to here we have 7.5, impossible. But 30, why not? So our x is 30. We know this. We know t is 3, so we can create a formula. 30, it's x, equals a, we don't know a yet, okay? T square is 3 square divided by 2. Okay, so a equals 30 times 2 divided by 9. It's 60 over 9. It's, I have calculated this before, 6.67. That's the value of acceleration. If we know the value of acceleration, okay, we can very easily find the g, because from this formula, g equals a, acceleration, divided by 0.326. But we now know a is 6.67 divided by 0.326. A simple calculation, a simple division gives us the result 20.45. This means that the gravitational acceleration on the planet was 20.45. It means everything was more than twice as heavy as on the surface of the Earth. And that's the solution of the exercise. Thank you.